Hey, we have here on the board today a really interesting integral from the MIT Integration Bee 2023. This is from regular season problem number 5. We have the integral from 0 to pi over 2 x cotangent x dx. Okay, I think there's quite a few ways we could approach this one, but for my method today I wanted to try integration by parts. I think it's going to transform pretty nicely when we do that. So what I'm going to do is we're going to do integration by parts using the DI method, tabular integration. And we'll just have our two columns. I'm going to differentiate x because that's going to differentiate nicely, and we'll integrate cotangent of x. Then differentiating x, we're just going to get a 1 here. And then the integral of cotangent x is just going to be natural log of sine of x. And I'm dropping the absolute value here just because we notice sine's always positive in this region. And then we'll get part of our solution right there on the diagonal. Okay, so we're going to have x natural log sine x, and we just need to evaluate that from 0 to pi over 2. And then this piece is going to be an integral, so this one's just going to be minus the integral from 0 to pi over 2 of natural log sine x dx. And this is exactly what I wanted, because this is kind of a familiar integral. I think I did a video on this integral, but maybe I did ln of cosine x. Okay, and before I continue, I'm just going to evaluate this. Plug a pi over 2 in here. Sine at pi over 2 is just 1. Natural log of 1 is 0, so the first term we could ignore. And then for our second term, we're plugging a 0 into x, which is going to 0 this all out. So this whole thing's going to 0. Okay, so all we need to do is actually do this integral, and we just need to remember this minus sign and keep that for our solution in the end. Okay, so now let's just focus on this integral here. We'll come back at the end for our minus sign. We know we don't want to forget that in order to get the right answer. And I'm just going to label this integral I, because I know that's going to be useful for this kind of problem. What I'm going to do for this is just make a u substitution. I'm going to use my bounds, and we're going to use the substitution u equals pi over 2 minus x. Then solving for x, we find that x is going to be pi over 2 minus u. Taking the derivative on the right side, we're just going to get a minus du. And then I'll make this substitution. So what's going to happen when I plug pi over 2 in here, we're going to have a 0 for the upper bound. We plug 0 in, we're going to have pi over 2. So notice we kind of swapped our bounds there. Natural log, and then we're going to have our sine pi over 2 minus u minus du. And from here, what I'm going to do, we're going to take the minus sign, bring it out front. We can use that to swap our bounds. And that's pretty nice because it's going to get us back to the bounds that we had originally, just 0 to pi over 2. And for this piece right here, you may recognize this. This is the complementary angle formula. So this sine of pi over 2 minus u is actually the same thing as cosine of u. So I think what I'm going to do while no one's looking is just erase this and enter in cosine of u here. But then one other thing I want to do here is I want to actually do a variable change. What I'm trying to do is add this to this integral, and we need to be in the same variable. We already have the same bounds, but we're in u over here. Because it's a definite integral, I can change my variable name. So I'm just going to change these u's and write these as x's, okay? This here is also I, because we've just kind of manipulated it. It's still equal to this. What I want to do is add these two together so that we'll have 2 copies. So this is going to be 2i when I add them together. So we're still going from 0 to pi over 2, and we're just adding natural log of sine to natural log of cosine. But by log properties, because this is addition, I can write this as a multiplication now, so we can multiply these two together, and this is going to be natural log of sine x times cosine x, okay, all within one log, dx. And then what I want to notice here is just the similarity to the double angle formula for sine. So the double angle formula for sine we have is sine of 2x is equal to 2 sine x cosine x. So kind of just making this happen, what I'm going to do is we're going to multiply by a 2 here, but then we'll divide by a 2 so that we're not changing it. Let's see if I still have some space on the bottom here. So when I rewrite this again, we'll use log properties. Because we're dividing here, we can write it as subtraction. So I'll write my first one, but for 2 sine x cos x, this again is sine 2x. So we're going to have one term, natural log of sine 2x, and then we're going to have minus. The other term is just going to be natural log of 2. Well, of course, I can break this into 2 integrals, right? So I'll just put in my bounds here. So we'll have this ln2 separate. So because this is just a constant, when we integrate this piece, we're just going to get x ln 2 that we just need to evaluate from pi over 2 to 0. Now when we evaluate 0, this thing's going to just be 0. When I plug a pi over 2 in here, we're going to get just pi over 2 natural log of 2. So I just need to clean up the board and rewrite this, but we need to bring this value over for this last integral here. Okay, so now with the rewrite, just notice I brought this value over from the last board. So again, this is 2 copies of the integral we're working with, and the integral is just this integral over here without the minus sign, which we're going to bring back later. So now focusing on this integral, notice that we're really similar now to like what we have over here. Other than the 2x, we've got the same thing as our I. Well, what I can do for that is just a u substitution. I just want to call u equal to 2x to try to get it looking more like this. So we'll say u is 2x, then our du is going to be just 2 dx. Well, I can create a 2 here so that we have exactly what we have for our du, but just bringing a 1/2 out front here. And then I can just make this substitution. So we're going to have our 1/2 in front. I'll take my pi over 2, plugging it in for x. Our upper bound is going to be a pi. And then plugging a 0 in, we just have 0 here. And we're going to have natural log sine of, now it's just going to be u du. And then now we have this where this is basically in the same form as this with a different variable, but the bounds change. So it's kind of frustrating, right? Because it's like we'd almost be done, but our bounds don't match this. What I want to do is fix these bounds to get back to pi over 2. So now I'm going to make another substitution, and instead of using another variable, I'm just going to go back to x because it's a definite integral. I can use whatever I want. So x is going to help me out here. So I'm going to make the substitution x equals pi over 2 minus u. Then u is going to be pi over 2 minus x. And our du value is going to be minus dx. Just so substituting one more time, we're going to plug our pi in here for u, and we're going to have a minus pi over 2 here. And then plugging a 0 in here, we're just going to have pi over 2, natural log. Now when I do my substitution here for u, we're going to have sine of pi over 2 minus x. But this is just the complementary angle formula again. Okay, so this is actually the same thing as cosine x. So just to save myself a step, I'm going to just write in here, put in here cosine of x. And then for our du value, we're just going to have minus dx. But what I can do with the minus sign, again, I'm going to use to flip my bounds just like I did earlier. So we'll turn that into a plus and that into a minus. Okay, and again, our upper bound matches this, but we don't have the 0 here. Well, the thing to notice at this point is this is actually an even function just because we have the cosine there. Because cosine of x is an even function, this whole thing is going to be an even function. And because we have an even function and symmetrical bounds around 0, what I can do is I can change the lower bound. We have this property, we can change this bound to a 0. And we just need to bring a 2 out front. But doing that 2 times 1/2 is just 1, so we'll cancel there. But now I think we're in good shape. As you may notice, this thing right here, this integral here is not the same as the I we have here, but it's the same as the I we did after our first substitution. So that was also I. So what we can say is this piece here is actually I as well. So knowing this is I right here, we can set up an equation knowing this whole thing is 2 copies of the integral 2I. We have 2I. Over here we have minus pi over 2 ln 2 plus I. What I can do is subtract an I on both sides. Okay, these are going to cancel out. This is going to give me just 1I over here. So this is almost what we need. So we just need to bring back that minus sign we had right there. So what I'm going to do is multiply here, the minus I here, minus here, and we've got our final solution, which is just going to be pi over 2 natural log of 2. So that's it. Thought it was a pretty fun problem today, so we'll stop it there. Thanks everyone for watching. Have a great day.